Hello, my name is Robert G. Hilster and I am your particle model guru, and I'm here to use the particle model to explain things in the universe and in physics, and in particular today we're going to talk about the right-hand rule. Now the right-hand rule is used in electrical work specifically to define the direction of a magnetic field, and in particular we can talk about current through a wire. We have a battery connected through a resistor to a wire and back, cause current to flow through the wire. We use the right-hand rule to define what the direction of the magnetic field around the wire is. Magnetic field can be clockwise or counterclockwise. But the right-hand rule tells you which direction it is relative to the flow of current through the wire. And this is important in knowing how to build electromagnets, and you can detect the direction using compasses and the magnetic needle in the compasses. At any rate, that's the right-hand rule, and that's using current theory that the electrical engineers use. Well, in physics or particle model, we're really interested in the flow of particle, and current flows in one direction, and they use the right-hand rule for that direction. But the particle model, or electrons, flow this way. G1 particles in the particle model flow the other way. You can see that the flow is still the same direction, and it's always that way in a wire that's carrying DC current this way, or electron flow this way. In the particle model, it's G1 flow this way, the field is that way. And it's always that way. It doesn't change arbitrarily. It isn't Thursday afternoon, it doesn't have magnetic flow this way, and then on Sunday morning it goes the other way. It's always that way, which means it's deterministic, and it's determined by the right-hand rule for the electrical engineer and the left-hand rule for the physicist or our particle model. And it's always that way. So something has to be causing that if it's so deterministic. Present physics doesn't have an answer. They don't, at least I haven't read one that explains why that magnetic field is that way. They just said, okay, just use the left-hand rule if you're a physicist. Use the right-hand rule if you're an electrical engineer. So somehow we have to determine what's going on inside the wire. Well, the wire is made out of copper, and the copper atoms are placed in a certain region, a certain order. So if I was looking through the wire at atoms of copper, I could have an atom of copper here and here and one here and one here, and I could have them placed this way. Got them placed not only vertically, this is vertical, this is horizontal, but I also have them spaced linearly, okay? So you've got these atoms placed that way. So if a G1 particle in place of an electron is flowing, it's going to bend towards this one, and then bend towards this one, and then this one, and then this one, and then back down. If you follow that path, you'll find it moving in a spiral order. So what the particle model is suggesting, that based on the copper atoms in this wire, the flow of electrons, or G1s, are actually flowing in a spiral direction. In fact, I did that wrong. The spiral is this way, which is like this. And so what happens is that these atoms are spiraling. If the got to get this straight here. Do it right, Robert. Got it flowing this way, and so it's going to be going around this way. It's flowing like this inside. that's true all the way through the whole wire. As big as the wire, if you expand the wire out, it's going that way through the wire, and it's going this way up here, and it's going this way down here. So it's going, all the G1 particles flowing through are going in this spiral. Now, some of them are trapped inside and they continue to go through. Others can actually escape. And when they escape, they're going to continue their spiral and go on out. And if it's spiraling the way I said, then you've got G1 particle flow this way, and it's spiraling. The one difference, the key difference, is that when you see it drawn in the physics book, you'll see that these magnetic fields are individual circles. I'm suggesting with the particle model, it isn't individual circle, that it is actually a spiral continuing on and going off into space. And the pitch of the spiral, the pitch of that path, is determined by the atomic spacing. Now, it may be each atomic spacing, which makes it very tight spiral, or maybe because it's moving at speed c through the wire, it's larger because speed tends to dominate. Anyway, you end up with a magnetic field because of that spiral path inside, and it's going this way, as I described. And as long as you keep the DC current going this way, or the G1 particles going that, keep it going, you're going to have this escaping and creating a magnetic field, which is not circular. We're predicting it's not circular, it's spiraling down and out at some pitch, which I really don't know what the pitch is. But that's the prediction we're making. And that's why we're saying it's deterministic, because it's the atom, the geometric spacing of the atoms inside the copper wire causing the electron to flow through. By the way, as a side effect, if you measure, if these particles actually had a wavelength, with DC you don't, but if you had a wavelength, normally you would see the peak of the wavelength enter and eventually leave, and the amount of time it takes divided by the distance gives you the velocity through the wire. But because it's not a linear path, the particle is actually traveling further than this, okay? And so that means that it appears like the electron is, or the G1 particle is moving slower than the speed of light because the path is longer. Just a side point, because that's what happens when things move through. You say it's light slows down through a prism. Why? Because it doesn't take a straight path. It flows, I don't know how it flows through light, but it doesn't necessarily flow in a straight line. Same way with copper. That's one of the ways the G1 particles flows through my body, through the earth, through a prism, through a copper wire. Does not flow straight. Physicists tend to say that that means that light is slowing down when it goes through a different medium. I contend in the particle model, the particle isn't slowing down. The particle is still going at c, it's just taking a longer path, which means that that you can either think of it as a shorter amount of time for that distance, which I'm doing the math wrong, but that's what makes it seem like it's slower. It is deterministic because of the orientation of the atoms in the copper wire. And that's the particle model's explanation of why the right-hand rule, and hence the left-hand rule in the particle model, is always deterministic, because you're always using a copper wire that is organized the same way, and the particle flows through it spirally, and they come out and go in that direction. Thank you for your attention, and hope you enjoyed it. And until I see you next time, this is Bob D. Hilster, your particle model guru.